as this is true for any combinations x, high, xj in these two invariant subspaces, you only need to average over these matrices. It's true for any particular vector. But matrices are tedious, there are zillion indices. So what we do is, we take two more matrices, rid of some of these indices. And when you construct a matrix, for example, if you write something that says H, I, J, and you have the representation here of a matrix D, A, I, this is really just a trace of the product of these two matrices, which here is called a character. And if this matrix is some representation, then it's character and representation. Continuous case. Character and representation U. U has to be the same representation, 1 over dimension. Remember, characters like inverses, we are integrating over the G, so the result only depends on F and H, and you get that that's the same as H, F, minus 1. It's called character orthonormality formula. You have lost something. It's much more elegant than what we started with, and much more abstract. But we did only trivial stuff all along the way, and you might think you lost something, but no. Of the character, your representation, dg, just from this definition here, you will find out that you get back the representation. So the great orthogonality theorem, which is impossible to remember because it has zillion indices and you have to get them right every time, can be much more compactly written in terms of characters. And it says if you have product of matrices here, product of matrices there, so H and F can be taken to be representations of other group elements in the same thing. When you average over the G, I'll just glue them together. So whenever you have average of a product of character, you just can replace them by a single character. So that's sort of content of character theory.